Okay, welcome everybody. So today we're going to discuss the second part of stoichiometry, which is using the gram formula masses that we practiced with a lot yesterday to do things like percent composition problems. So let's take, for example, if you had something like KNO3. And I asked you, well, what's the percent by mass of potassium in this compound? And well, just like any other percent, it's always a part over a whole times 100. So we would do the mass of the part, the mass of K, over the mass of the entire compound KNO3 times 100. Well, now I can look up the mass of K. The mass of K is 39. The mass of the entire thing would be 39 plus nitrogen is 14 plus 3 oxygens is 48. And this would give us our total on the bottom, and then we would times this by 100. And so when we do this, we could get our total. So if we did 39 divided by 39 plus 14 plus 48, we would get 39%. So we would get around 39%. Now this is just a coincidence because it turns out that the gram formula mass is pretty much out of 100. But the process would be the same. Now there's something called hydrates, and we can do percent composition of hydrates. With percent composition of hydrates, we would have something like this, CuSO4.5H2O. Now a hydrate has this water molecule associated with it. I know that this looks like a multiplication sign, but in reality it's not a multiplication sign, it's really an addition sign. And so we can find the masses of both of these. So we have the mass of copper sulfate, that would be 160 grams. We have the mass of the 5 waters, that would be 90 grams. So if I wanted you to find the percent composition of water in this, I would do percent of water is equal to 90 divided by 160 plus 90, which is 250. Times this by 100, and then I get 36%. So that's showing you that there's 36% water. Now, on Thursday, we're going to do a lab where we actually experimentally find the percent of water in the compound. And so that looks something like this. Let's say, for example, that we had, 10 grams of a hydrated salt. And to get the water out, we have to do something. So what we're going to do is heat this. So if we heat this, let's say that we're left with 8 grams of what's known as the anhydrous salt. So now the question becomes, and this is where people get tripped up, how much water was evaporated? Well, hopefully you see that you can subtract the two. And so what we'll have is we'll have 2 grams of water evaporated over the 10 grams of the total hydrated salt that we started with times 100. And we'll end up with 20% of water. So we'll practice a bunch of these in class, but this is kind of, the 2 types of percent composition problems you'll see. If we include the experimental one, it's really 3 types of percent composition problems. So now, let's talk about empirical formulas, which relate to percent composition. So when we have an empirical formula, first let's talk about what it is. An empirical formula is defined as the reduced formula. It has the lowest whole number ratio of elements in a compound. And so what we're going to do is we're going to see if we have something like C6H12O6, what's the empirical formula for that? Take a second, try and work it out. How can I reduce those subscripts? Well, if you pause this and you try it out, you'll see that it's CH2O. I divided all of them by 6. This is my empirical formula. So this is my empirical formula. This formula over here is called my true formula. It is also called a molecular formula. So we have our true/molecular formula. and we also have our empirical formula. So, these are the two types of formulas, but you'll be given problems where you'll be asked to find the empirical formula. And so that will look something like this. I could give you, for example, the percentages that are present in a compound, something like 75% carbon and 25% hydrogen. And to do this, we use 3 easy steps. The first thing that we're going to do is we're going to assume it's 100 grams. So we're going to have 75 grams of carbon and 25 grams of hydrogen. The next thing that we're going to do is we're going to convert those to moles. So step 1 was percent to grams. I'll write that over here. The next thing is grams to moles. So to change carbon from grams to moles, I times it by 1 mole over its 12 gram formula mass, and I get 6.25 moles. Now I can do this with hydrogen, so I can do times 1 mole over 1 gram, and that gives me 25 moles. At this point, I do have a formula. My formula would be this, C6.25, H25. The problem is that you need the lowest whole number ratio in order to be an empirical formula. So we need to reduce these down to whole numbers. We do that by dividing by the smallest number of moles. When we do this, we get C1H4, or just CH4. So the last step is to divide by the smallest number of moles. Now, if you don't get a whole number, if I got something like C1H2.5, you can't reduce it again. You'll keep getting fractions, so you would double it, and you'd get C2H5. So, this is a type of problem where we have an empirical formula here from a percent composition. I could give you another problem to practice, and that would look something like this. So let's say it has carbon, hydrogen, and oxygen. Let's say that we have 40% carbon. Let's say that we have let's say we have 6.67% hydrogen and 53.33% oxygen. So take those percentages, follow the steps, percent to grams, grams to moles, then divide by the smallest, and figure out what the empirical formula is, and let me know tomorrow what you get. Okay, there's also the situation where you'll be asked to find the molecular formula of a substance. And that, what you do is, you take the empirical formula, and you use that to figure out the molecular formula. The key to understanding this problem is that the molecular, it's always a multiple of the empirical. So what do I mean by that? Let's take something like if I were to have CH. That's an empirical formula. I can't reduce it. Well, if I had C2H2, that's a multiple of it. How did I go from CH to C2H2? I timesed it by 2. I could also have this where it could have been C3H3. And that would have been timesed by 3. I could, have any multiple times by 6, C6H6. And that would have been times by 6. These are all molecular formulas. They all can be reduced back down to CH, and they're all multiples of it. Now we also see this in the gram formula mass. So something like CH here, it has a mass of 13 grams, if we look on the periodic table. C2H2, it has 26 grams. C3H3, it's 39 grams. C6H6, that's 78 grams. And so look at how that works. If I take 78 and I divide it by 13, I get 6. It tells me the multiple. Let's try an example. Let's say that you had CH2O as your empirical formula. And they tell you that the true mass is 180 grams. Well, let's find the empirical mass. The empirical mass is going to be 30 grams. Well, how does 180 and 30 relate? Well, let's divide them out. 180 divided by 30 is 6. So what does my true formula have to be? Well, if you said C6H12O6, then you're right on, because you had to times that original one by 6 in order to get the true formula. So this is how you do molecular formulas using an empirical formula we'll practice. Now what we're going to do next time, and we're going to start this next week, because this week we have practice for this. We're going to do some labs. We're going to have a quiz, practice some more, and then we're going to do types of chemical reactions next week and talk about that in our next video. All right, thanks so much for watching.